So today we're learning about the pH scale. Again, these are things I wanted to do here in school because they're a little hard to do at home. And I'm going to be doing some other lessons to help you understand how do we calculate pH and what does that mean. But I wanted to introduce this awesome idea of pH indicators. And if you guys remember that very first day of school, I played with a bunch of different liquids, and we turned water into wine, into beer, into milk. Almost all of that was acid-base types of reactions, and just using different types of pH indicators to play those tricks. So whenever we think pH, what you want to remember is, Zoe, if you could help zoom in again, that our scale goes all the way from 0 to 14. 0 to 6.99, I mean, technically if it's not at 7 yet, then it's not neutral. So anything under 7 we would consider acidic. And we're going to learn that what that really means is the concentration of hydrogen ions that are available in that solution. So when we say pH, and you'll see that in the lesson eventually, that's talking about the concentration of hydrogen ions. Neutral means that there's not an over amount or an under amount, is going to be 7. Now anything that has a pH greater than 7 means we really don't have a lot of hydrogen ions. Remember, hydrogen ions define an acid. So our bases then are 7 to 14, which means we don't have a lot of hydrogen ions, we have a lot of hydroxide ions that are in there. And I'm going to, again, we'll talk the math later, but I just wanted to take a moment to show you some different pH indicators. So I got 3 different things that I'm going to attempt to set up. These are 2 different solutions. So right now I have this sponge that has been soaked in some pretty crazy types of chemicals that makes it look red. And it's sitting right now in an acid. So if you see here, we have it in hydrochloric acid. So we have it in a strong acid. Now I'm going to take it and I'm going to move this sponge into a solution that has a base in it. So this sponge has been soaked with an indicator. So Zoe, if you could zoom in on this for them, they can see that this is sodium hydroxide. So this is a strong base. Now remember, the cool thing about a pH indicator is it'll change colors depending on the acidity of the solution. So this is a very basic solution. It's going to turn the sponge, it's really a really deep dark blue, almost to the point of black. But if I put it back in my acidic solution, that pH indicator that is soaked on that sponge turns it back into a red sponge, and some of the pH indicators actually going into the solution as well. So the sponge is actually what is soaked in these different things. So that's one thing. I'm going to move over here next. Ooh, I forgot oh no, wait, I have it right here. So do not do this at home, you guys, because we don't have strong enough acids to do this. Now, I have a whole range of acids, and Zoe helped me fill these up, and honestly, in the meantime, I broke her phone. I actually stuck it in the vacuum pump because I was trying to talk about how sound waves don't need air, and there's a chance that I actually broke her phone. So before we did that, we were doing, getting this ready, and we don't remember which side is which. So we think that this is the most concentrated, like the scary, strong hydrochloric acid, and we think that this is the least, but it really doesn't matter because I'm going to attempt to drop just 1 drop of plain old food coloring. So some things in our home could actually be a pH indicator if we had strong enough acids. Now I really hope you guys don't have something like hydrochloric acid sitting around. Evan, you being the garage guy that you are, this is muriatic acid. This is the stuff you could buy at Home Depot. So Home Depot sells it as muriatic acid. It's really just hydrochloric acid. So I'm going to put 1 drop in each, and Zoe, feel free if you want to zoom in a little bit. And then I'm going to go back. Oh, I think it's flipped the other way.
Is it?
Yeah, it's fine.
Turn it the other way.
I will. So I'm going to spin it around the other way because that's telling me based off of what I know. And this is just the crazy thing, you guys. So food coloring, just plain old blue, it only works with blue food coloring. Depending on, probably should actually start here and work my way down. The acidity of the solution will change different colors. Now we can almost get the entire color of the rainbow out of this. Okay, I'm missing a little bit of some yellows in there, and maybe I don't see a strong purple, but I get a nice little rainbow. Let me get a piece of paper behind it, you might be able to see it better. But for this, she's laughing at me again. So this was my least acidic. This was like a 0.1 hydrochloric acid. And then we went all the way up to, I think our most concentrated is 12 molar. So we went like 0.1, 0.5, 1, 3, 6, and then 12, right, Zoe, or something like that? So something really close to that. So food coloring is acting as a pH indicator here. Based on the pH, it's going to change different colors. Now this one's a really cool one. If we go back to this guy, it can only do 2 colors. So it can be red or it can be blue. This one can have a host, so it can do a better range of pHs because different colors indicate different pHs. I'm going to do another one that's pretty slick as an entire range. So she's making fun of me again. So this you might find this in your grandma's closet. This is milk of magnesia. I didn't put the lid on when I shook it. I always tell my kids to put the lid on their orange juice. Like, I don't know how many times they're pouring orange juice in the morning, and then all of a sudden they like try to shake it, and it's like an orange explosion everywhere. I'm like, there's this thing called a lid, but I just like spilled milk of magnesia everywhere, so it's fine. So I'm going to take a little bit of this, about 20 mils or so, which I don't really know how much that is, and who really needs to measure nowadays. So there we go. So if you look right here, zoom in, Zoe. Magnesium hydroxide, look at that science, you guys. So right now it's telling you it's a base. At this point, you might even recognize, hey, that's a weak base. It doesn't totally dissociate. Now I'm going to do something else. There was water that was in here. You guys know there's a little stirring rod because I'm too lazy to do it myself. And a lot of times, the colder the temperature, the slower the reaction. And I want it to go slow so that we can see the color changes that happen with this. So I'm going to put some ice in there. And I have a synthetic universal indicator. But purple cabbage, if you take it and you boil it down, the liquid that comes off of that purple water that comes off, will do this same thing. Now don't do this without your mom knowing because it smells horribly, and maybe she was going to put the cabbage in dinner that night. So I'm going to take that universal indicator, put a few drops in here. And the pH indicators are not really being used up in the reaction. They're going to show us what happens. This last unit that we talk about is called equilibrium, and pH indicators are used in an equilibrium equation, but they're not the active guy in this. They're just going to show a color change. What I'm going to add to the magnesium hydroxide is hydrochloric acid. So I'm just doing a neutralization reaction. You just learned about writing net ionic equations, so think this is a strong acid reacting with a weak base. So what we want to zoom in on, Zoe, is we're going to see what happens whenever we added. This universal indicator kind of does what the food coloring does with the acids in the test tube. It should go through kind of a host of colors. Okay, so let's put some in here, and let's watch what happens. All right, so again, it's going through this host, and it's slowly kind of getting back to that blue color. And I can continue to do this until I have too much hydrochloric acid and there's no more magnesium hydroxide that's left. Now, magnesium hydroxide is not very soluble in water, and you kind of saw that whenever I poured it out. So let's add some more. Try to get to that pink. And again, watch what happens. So it's going through that host of color, that rainbow of color, but every time it doesn't get pushed all the way to that purple or to that blue, where eventually we're going to shift this solution to have that pH that's acidic. That's going to be represented by the red. Okay, so again, it's getting there. Now we're seeing it kind of hang at the yellow. And if I was really patient, I could do this drop by drop until it's at the pink and it stays at the pink. Not quite there, so let's add a couple more drops. And again, and now let's finish it up. Okay, so notice another thing that happens that you sass, this is like you kids, I tell you to sit down and you just stand up 5 seconds later. I'm gonna put your phone in the vacuum pump next. All right, now I think I'm good because not only is the color staying like that, but take a look. We started off and it was cloudy. So if you were to describe this now, I know you'd still say it's kind of pink, but is it cloudy or clear?
Clear.
Clear. So hydrochloric acid is an aqueous solution. It's very soluble in water, but milk of magnesia is really a coarse suspension. And we can tell that. Like whenever I look at this, when I pour this stuff out, it doesn't look like it's dissolved in anything. It's going to be very opaque. Solution should be clear, like how hydrochloric is. So it started off as just a suspension, and then as the magnesium hydroxide got more and more reacted and got neutralized, we end up with a solution because now we have excess hydrochloric acid in here. Now, if we wanted to have a little fun, I could probably throw in, this is that base, so let's just see. And my guess is we can get it to go back to more of that blue side. Now I've got a strong acid, strong base. It's going to be hard for it to go anything in between, but we can show the actual indicator did not get used up here. Indicator stays, but it's the acid in the base that changes the color. So we put the acid back in, and it's going to go back to pink. Harder to show those in-between colors with strong acids and strong bases. We could do it again, though, with using a weak base. Okay, I should have worn gloves. My hands are on fire. They're burning. I had acid all over them, so I'm going to be done. And remember, practice safety, which I did not do today. Sorry. Bye, guys.